It's 3:01. I'm starting a minute late.
Oh, wow. That's interesting.
So we have a visitor today. It's Professor Irwin. So we're going to have visitors on Monday and Wednesday next week as well. It's part of my evaluation process. So make sure you're getting good quality education. So I'll be on my best behavior, of course, not the usual shenanigans that I always engage in. Yeah, we have 11 students registered, and there's usually everyone shows up, but I will have to move on. Does anybody have any questions about anything before we start? Anything? Nope. Okay. So where we're at right now, we're in thermodynamics. So we're studying thermodynamics. And we talked quite a bit about entropy. So what entropy is, how it's defined, basically it's probability. And also the second law of thermodynamics, basically saying entropy of the universe is always increasing, and that's one of the things that drives many things forward. So let me talk about a new topic about Gibbs free energy, and let me just define a term here. So Gibbs energy, G, is defined by H enthalpy minus T temperature times S entropy. And maybe even more important than that, delta G, change in Gibbs energy, is equal to change in enthalpy H minus T, change in entropy delta S. So do you guys like have you ever watched The Big Bang Theory? I like that show. You haven't seen it, Jay? So, but are you familiar with the person Sheldon in the show? Or okay, so Jay, you don't know Big Bang Theory. Sheldon is he's basically a super awkward nerd who's probably has like Asperger's syndrome or something like that. Gibbs, the actual person, he apparently was like that. He liked to sit in a dark room and just do derivations, and no one liked him except for one person. It was Lord Kelvin, and Lord Kelvin from Kelvin temperature, and they went to a faculty party and Lord Kelvin was there. It's like, where's Gibbs? And like faculty, Gibbs. It's like. So he's so weird to talk to you. Like, well, you read his stuff? It's brilliant. And Kelvin apparently was allegedly used his abilities, his sway to help Gibbs out and help him politically. But Gibbs, he sat in a dark room and just did derivations all day. I'll show later. Gibbs energy is connected to equilibrium, and this is a big thing since you can connect equilibrium to thermodynamics. We can understand many, many things about them both, and you can calculate them. This is different to kinetics. So kinetics is something that we cannot just outright calculate and figure out. We have to do it experimentally. But thermodynamics and equilibrium, they're related, and therefore we can figure them out exactly, which is very, very useful. So let's go back to talk about Gibbs. So not the person, but the energy. So if Gibbs energy is less than 0 or negative, that means that the process or the reaction will be spontaneous. Spontaneous means it just happens on its own. If it's less than 0 or positive, that means it's non-spontaneous. It's not going to happen unless you force it to. And if Gibbs energy is equal to 0, that means the system is at equilibrium. So delta G is very important, and let's talk about this in certain processes. So with this, so here on this graph, I've written delta H on the y-axis and delta S on the x-axis. So this here, delta H is positive, delta H is negative, delta S is positive, delta S is negative. So remember, for delta G being negative, it's always spontaneous. So if delta S is positive, delta H is negative, that means we have a negative number and a minus a positive number. Temperature is always positive because it's in Kelvin, so temperature is absolute. So that means things in this condition are always spontaneous. So an example of that is like combustion of propane and oxygen. So combusting propane and oxygen is exothermic, and you evolve more moles of gas. So that means at any temperature, propane will burn. That doesn't mean that it's going to happen quickly. It just means it's always going to happen. And non-spontaneous, well, so this is when delta H is positive, endothermic, and delta S is negative. That means it's becoming more ordered. Remember, entropy means disorder. So this could be the opposite. This could be carbon dioxide and water turning into propane and oxygen. Something else like rust, so rust, iron oxide turning into iron, metal, and oxygen gas. That will never be spontaneous. Can it happen? Yes, but you have to force it to. So that's how we crack ore, right? So we get iron, we take rust, we heat it up in the presence of carbon. So we can do that, and we can get iron from rocks, from iron ore. But that doesn't mean it's going to happen on its own. It just means we have to force it to happen. Okay, so high temperature. High temperature, what is this quadrant? We have delta H is positive, delta S is positive. So it means it's endothermic. Do you have a question? S is entropy. S is disorder. So this side here, positive delta S means more disorder. So this is more ordered. Things tend to become more disordered. Think of a messy room, right? It's easy to have a messy room. It's not so hard to have a clean room. The room just kind of gets messy on its own. So the example of this would be something blowing up and vaporizing. So if I add anything to a high enough temperature, if I take something like a hot dog and I throw it into a furnace, it's going to fly apart if the furnace is hot enough. So what's keeping like the proteins and whatnot together, that's enthalpy, that's H. It stays together because it likes to be together and it releases heat when it forms chemical bonds. But if the temperature gets high enough, entropy will take over and all the atoms will scatter in space. Low temperature, so this is where delta H is negative exothermic, but delta S is also negative. That means more ordered. This is why ice freezes or water freezes. So when water freezes, it forms a structure, and then with the intermolecular forces, and when it does that, it releases heat of fusion. So solids are low in entropy. They're very ordered. So entropy says everything should be a gas, but when a bond happens, energy is released. This is this quadrant right here. So this tells us more than just plain old entropy because it includes enthalpy as well. Okay, so the other thing about these things, entropy S is a state function. So is Gibbs energy. So is H enthalpy. So is E internal energy. So is A Helmholtz free energy. We don't talk about it in this class. So we don't have anyone here in Calc 3 or 4, do we? No one's gotten there yet, right? We only have people in Calc 2, I think. So eventually, when you get to calculus like further, you'll learn about partial differentiation. Oh, you've studied that? Okay. So a state function means it's an exact differential, which means that it's the derivative with respect to x and then y is equal to the derivative with y with respect to x. The other thing you can say, it doesn't have any non-linearities in the function. It means it's a state function, which means it's path independent. So path independent, so that means it doesn't matter what path you take, you always get the same answer. So do you remember the first law of thermodynamics? Delta E, the exchange of internal energy is equal to work plus heat. There's more, but that's simplified for chemistry. Work and heat are path dependent, so they do not have direct or perfect. They don't have the derivatives. They don't have exact derivatives. So meaning, if I take a gallon of gasoline and I burn it, if I just outright burn it, I can get all the enthalpy. I can get heat from it. I can also take the gallon of gasoline, I can put it into a car and get 20% of work out of it. I can also put it into a hybrid car and get like 40% work out of it. Of course, the rest is heat. So the work and the heat they do not necessarily have to be the same thing, but the amount of energy that I get from gasoline does not change. If I burn it, the amount of heat that I get of just heat will be the same as the work plus heat in any car that I put it into. So with this being a state function, so entropy and the rest being state function, Gibbs energy being state functions, it's easy to calculate things. So we have tables of these things, of these terms, and then we can use those tables. It doesn't to calculate things. I told you that eventually Gibbs is connected to equilibrium, and we'll talk more about that later. But that's nice because then you can just look things up. There's an old saying that if you can spend a day in the library and that'll save you a month in the laboratory because you can look things up. It's not only just looking things up. You have to be able to go and then use the knowledge and calculate it out. So, and we already talked about the third law of thermo. So the third law of thermo is that it's just kind of a trivia question, but have it in there. How are we doing so far? Any questions? Man, where is everyone? Okay. So we're still talking about entropy. We'll get into Gibbs again soon. Oh, you can't see that. Okay. So let's talk about entropy, and where I'm going to go more is talk a little bit more about what entropy means. Here is the standard. So the 0 means standard, if you remember from 161. That means standard entropy and here's the noble gases. So if helium here, and as it gets more massive in a xenon, and generally speaking, the entropy increases. So let's talk a little bit about what this means. Yeah, they are low. Yes. Noble gases ones. Not necessarily because the noble gases are stable. It's just because they're just spheres. Okay. Do you remember what temperature means? Definition temperature. Temperature is average translational kinetic energy. You remember that? So did you cover that in 161? Different types of energy. Well, that could work. Yeah, but it's translational kinetic energy. So right now I'm moving very translationally. Okay. Can I move it? Is there any other way I can move? Yeah, rotational. Any other way? That's still translational. I can vibrate. So if I have just a sphere, so this only has translational energy. It doesn't have, so water, so oxygen, hydrogen, it can rotate. It can vibrate. Okay, but a noble gas only has translational. And which is also kind of cool about this is kind of an aside, but if you see, for a given amount of energy, the more massive the atoms have more closely spaced energy states. So since xenon is more massive, it has a higher momentum, therefore its energy states are closer. That's the reason why the entropy for xenon is higher. But even written between this is a proof for the quantization of space-time. So have you ever heard of Zeno's paradox before? That's if I'm going to get to the desk, I'm going to go half the distance, half the distance, half the distance, half the distance. I will never reach the desk. That's Zeno's paradox. The thing is that space-time itself is quantized, meaning it only exists in certain packets. They'll get to a point where I will, in fact, touch the desk. At least the quantum state of being of the desk versus my finger or foot will be right up next to each other. So let's say that Zeno's paradox wasn't true and that there was an infinite number of states between point A and point B, okay? So that would make entropy pretty much irrelevant because there's an infinite number of states, which means that remember entropy is Boltzmann constant, natural log, number of states. If that number of states was infinity, the entropy would be infinity. So the fact that these actually have entropy and there's only one place to put the energy which in temperature is the translational energy, that shows that space itself has structure. So this is kind of beyond the class, but I think that's interesting. So okay, so noble gases just have translational energy. So let's compare it to something else. So argon and nitrogen monoxide. So they both have about, argon is more massive. So using this argument up here, right? So since argon has more momentum, it should have more closely packed energy states, therefore have higher entropy. But the entropy for nitrogen monoxide with 30 grams per mole actually has a higher entropy. Why is that? Not so the structure. It's the fact that it has translational, vibrational, and rotational. Okay, so think of it this way. Say I have $1,000. Okay, and there's one person. The $1,000 can only be carried on as cash. Okay, and another person has $1,000, and that person has a checking account and a savings account and cash. So it has a big wallet, checking and saving. So argon is like the person only has cash. Okay, it's only one place to put the money, one place to put the energy. Nitrogen monoxide can put the money, put the energy in cash in a wallet, and a savings or a checking account. And remember, entropy is the number of states. So the more states that you can put things in. And the other thing to note, it's per mole. You're like, what about one argon? We're talking about 6.02 times 10 to the 23rd. So if you give 100 joules to a mole of argon, the argon can spread its energy out. And it's in a distribution. Remember, with kinetic molecular theory, it's a distribution of that. So it can only do it in temperature. But nitrogen monoxide, it can put it into its vibrational and rotational state. Therefore, it has more places it can put things. So that's the reason why the entropy is higher. Is that making sense? No, not really?
No, it is.
Okay. Yeah. So it's entropy. Entropy is just its chance. It's how many possibilities there are. So since there are more possibilities, it has higher entropy. Okay, so some more equations. So remember when I said that entropy and Gibbs were state functions and they're path independent? So, which means you can calculate them out. So, and I give you these equations as well, so you don't necessarily have to memorize them. But the change in entropy for a reaction is equal to the sum of the number of moles of the products, entropy of the products, minus the sum of the number of moles of reactants, entropy of reactants. So you're taking the final minus initial. So it's final minus initial. And this works for all state functions. So do you remember in 161, you had that for H, for enthalpy. And you had that for E, internal energy. And you can have it also for G and S, and Helmholtz free energy A if you ever take classes with that. So any state function will do that. Same thing with Gibbs free energy here. Final minus initial, same thing as with the entropy. And also, there's going to be, you're going to see this a lot, the delta G, getting the delta G reaction, because the delta G gives you lots of information. If it's negative, it'll happen. If it's positive, it won't happen if it's zero at equilibrium. And if it's at equilibrium, then we can calculate things associated with that equilibrium.
Can I ask a question?
Please.
On the table above that, where you were showing the difference in entropy and then the sensation, how would you calculate that? Would you build how would you know by looking at those two which one had a greater entropy? If you just
Oh, you mean without a table?
yeah.
You would likely go for not the noble gas because it's just they tend to have low. That's the first hint. I mean, if you look at xenon up there is 170,
Mm-hmm.
and nitrogen monoxide is a very simple molecule, just 2 atoms.
Mm-hmm.
So I mean, right away you would think noble gases. You think it's not reactive, and they have low entropy, kind of thing. So that's hint number one. Hint number two, you could calculate that out by using this equation. The entropy is equal to the Boltzmann constant times the natural log of the number of states. So, and you can then multiply Boltzmann constant times Avogadro's number. And actually the Boltzmann constant times Avogadro's number is equal to the gas constant R. So if you want to do Bohr moles, you could do R natural log number of states, and it's capital omega. So you have to figure out the number of states. For the difficult part with that is then figuring out your number of states. So.
Most of you have to be told. Usually you're going to be looking at a table.
Yes. Yes. Other questions? Okay. So let's do an example here. Ooh. So we want to calculate the standard change in free energy for a reaction. So we have this reaction here, SO2 plus 1/2 oxygen gas makes SO3. Calculate the delta G reaction at 25 degrees Celsius and determine whether the reaction is spontaneous. So first of all, this reaction is improper because you have a half of an O2. Okay, so the O2 should be whole numbers, right? It should be 2 SO2 plus O2 makes 2 SO3. But and here are the tabulated data, and we know that that the delta G is equal to delta H minus T delta S, and we're given the H and the S, the standard H's and standard S's. For H is enthalpy, S is entropy. So another thing to note, so S entropy is absolute. Okay, entropy, just like temperature, is absolute. Gibbs energy, all the other state functions, Gibbs energy, Helmholtz internal energy, and enthalpy, they're all relative. So we always pick a relative scale for that. So that's why it's delta H and S is just S. Okay, so, and if you remember standard state, the enthalpy of an element is 0. So that's why oxygen is 0. It's just, we pick that as the 0. Okay, so, I should, also the change in entropy reaction, it's going to be the sum of N of products, S of products minus the sum of N reactants, S reactants. Okay, so let's apply the equation. So delta H first. Delta H equals the products, I guess it is 0 formation SO3 minus the quantity, 0 formation SO2 plus 1/2 H of formation O2. And if you see where I'm getting this, so SO3 is a product, it comes first, 1. SO2, these are the reactants, and there's only one, so I don't have it in brackets. There's 2 reactants, 1 for the SO2, 1/2 for the N for O2. Of course it's 0, so it goes away. So this equals SO3 right there, minus 395.7 minus 296.8 plus 1/2 of 0, like that. And this equals so 5.7 296.8. This equals minus 98.9 kilojoules per mole. And then the delta S, same idea. It's the S0 SO3 minus the S0 SO2 plus 1/2 S0 O2. Right, so it's the same, delta S is the same argument, but using S entropy. And so then now we have this equals 256.8 minus the quantity, so 248.2 plus 1/2 205.2. And this equals 205.2. So this is then minus 94 joules per Kelvin. The units on well, it says per mole, per Kelvin mole. So units on entropy are joules per Kelvin. Now we take these data, and we have delta G is delta H minus T delta S equals 98 minus 98, 900. I usually get rid of the kilojoules. So think of the units. Kilo means 1,000. Minus temperature, 25 degrees is 298 Kelvin. Minus 94 joules per Kelvin per mole. So putting this in our handy dandy calculator, minus 900. So minus minus a plus, 298 times 94. And we get minus 70888 joules per mole equals 70.9 with the sig figs kilojoules per mole. So this is delta G right there. And since delta G is negative, it's spontaneous, meaning this will happen at 25 degrees Celsius. Okay, so recap. Let's talk about this example. We have, actually, before, anybody have any questions? Okay. Recap, we have this equation, SO2 plus 1/2 O2 making SO3, and we have these table of data. So we want to know what the delta G of reaction is, so that's the free energy available in this reaction, and then also to know if the reaction is spontaneous or not. So what we do is we employ the fact that H enthalpy and S entropy are state functions, so we can do the final minus the initial to figure out what the change in each for the reaction is. And then we can take the H and the S and put it into delta G to figure out what the Gibbs free energy is. So we do this here, and note again that so it's SO3 is a product, it goes first, and there's one of them. Then the SO2 and the O2, 1/2 O2, keep that as the coefficient for the n. Keep that in, and we calculate out the enthalpy to be about minus 100, and the entropy to be about minus 100 kilojoules per mole for the enthalpy and joules per Kelvin for the entropy. And then put in the equation delta G is delta H minus T delta S. And one of the most common mistakes is that delta H is in kilojoules per mole. So I always just write it out in joules. So that's the most common mistake there. And then we get minus 70. And since it's minus, negative delta G means it's spontaneous. Anybody have any questions with this? Okay.
Negative delta G is spontaneous.
Yes, negative delta G Negative delta G means spontaneous. Positive means non-spontaneous. Equals 0, equilibrium. Spontaneous means like iron rusting. If you put iron out in the air, it's going to rust. That's spontaneous. Rust turning to iron, that doesn't happen naturally. That's non-spontaneous. But you can force it to happen using energy and other reactions. Okay. So now your turn. We have 2 calcium metals plus oxygen gas making 2 calcium oxide solid. Here is the delta H for the reaction. There's delta S for the reaction. And then what is the standard Gibbs free energy for this reaction? Delta G.
What's that temperature?
The standard is 25 degrees Celsius, 298 Kelvin.
That's a negative in front of the entropy rate.
Entropy is negative. You're going from a gas to a solid. It's negative. No, highlight. There you go. Big fat negatives. Yeah, I know it's hard to see sometimes. Anybody getting stuck? How many people think it's A? How many think it's B? How many think it's C? How many think it's D? We got 3 out of 5 going for C. Do you guys, Jay, Kenji, do you have any questions, or are you following? The answer is C. Are you?
Oh, I didn't put the negative.
Okay. Jay, do you have any questions, or? Okay. Or did you vote for C? I didn't. All right. You just have to put in the, so delta G is minus 1,269,800 minus a minus 298 times 364.6. If you do that, you get minus 116,1149.2. So which then is C by times 10 to the 6 joules. Questions with this? Okay. All right. You probably remember this from 161. Do you remember studying Hess's law? Okay. Comet remembers. Okay. Well, if you notice, there's many things the same. So if a chemical equation is multiplied by some factor, then delta G reaction is multiplied by the same factor. So if I can get 1,000,000 joules out of a gallon of gasoline, I don't know if that's how many I get, but let's say I get 1,000,000 joules out of a gallon of gasoline. If I get 2 gallons of gasoline, I get 2,000,000 joules. If I have a half a gallon of gasoline, I have a 500,000 joules. Okay, so whatever you multiply some factor, you multiply by that factor. So a chemical equation is reversed, delta G changes sign. So if I require 1,000 joules in photosynthesis, so photosynthesis is carbon dioxide, 6 carbon dioxide plus 6 water makes glucose and 6 oxygens. If I need 1,000 joules to do that, if I burn glucose in the presence of oxygen, I get 1,000 joules back. So one direction is positive, so it takes energy to form sugar, and then if I burn sugar, I get energy back. Energy is negative. And then number 3, if a chemical equation can be expressed by the sum of a series of steps, then delta G for that overall reaction is the sum of the free energies for each step. That is known as Hess's law. So actually Hess's law is specifically for enthalpy, but it's the same idea. Okay, so let's do this for this example. What is the delta G reaction for this? This is the formation of propane from 3 carbons and 4 hydrogens. So, of course, as Professor Irwin pointed out, we probably just look this up in a table. So, but we, and this one's pretty easy. This is where a day in the library will save you a month in the laboratory. I mean, can you imagine trying to measure something like this? This would be painful. It would be easier to measure the enthalpy H than the entropy. The entropy you could look up, but I mean, this would be a horrible experiment to do. So if you couldn't find it right out, say it's something a little more complicated, then this is when you have to employ Hess's law to figure things out. In this class, you will be given all the pertinent equations you need, of course. In the real world, though, or the real world probably is actually academia. Well, I don't know. You could do this in industry. You would have to seek out the equations, and there's a bit of strategy for it. So for me, when I do this, I always start by writing the equations and putting the products on the right and the reactants on the left. So I look at this equation here, the top one. Here, let me zoom in here. So I look at this equation. So C3H8 propane is a product, so I know right away I'm going to flip this one around. The second equation, carbon plus oxygen makes CO2. I'm going to leave that as is. I'll probably multiply by 3 because there's 3 carbon there. And then hydrogen, I'm going to leave it as is because hydrogen's a reactant. It's on the right side of the equation. And I'll probably multiply by 2. The other strategy is I need to get rid of the intermediates. The intermediates are carbon dioxide and water in these cases. Okay, so let's write this out. So I'm gonna flip this one. 3 CO2 plus 4 waters makes propane and 5 oxygens. Okay, and since I flipped this and I don't like writing out the numbers, I just assign them variables for now. So since I flipped this one, this is minus G1 because I flipped it. Okay, then I'm going to leave the other ones as is. Carbon plus O2 makes CO2, that's G2. And then 2 hydrogens plus oxygen makes 2 waters. And this is G3. So there's 2 ways. So the next thing I have to do, I have to get rid of the intermediates. You can look at it as I either want to get the number of reactants to be the right amount. So right now we have propane on the products, and we have carbon and hydrogen on the reactants. You can either look at it as I want to get the right number of reactants, or you want to look at it as I need to get rid of these CO2s and waters. I tend to look at it as get rid of the intermediates. So for this equation here, I'm going to multiply it by 3 to get rid of the CO2s. And I have to multiply that by 3. Or you could also look at it as I need to have 3 carbons. So both logic points work. And same thing with the water. I need to multiply this by 2 to get rid of those 4 waters. And then now you can add them together. And notice the waters cancel. The CO2s cancel. And right here, 3 plus 2 is 5. Those cancel there. Okay, and what I'm left with is 3 carbons plus 4 hydrogens yields C3H8. And this is minus G1 plus 3G2 plus 2G3. And then I just put in the numbers. So G1 is minus a minus 2074 plus 3 minus 394.4 plus 2 minus 257.1. Then you put that in your calculator. 2074 minus 3 times 3, 4.4 minus 2 times, oh wait, I said 2 is 4 times 4, 57.1. Then I get this equals minus 23.4 kilojoules per mole. And then that's your answer. Okay. So recap on this one. We have this equation. 3 carbons plus 4 hydrogens makes propane C3H8. We don't know what that is, but we're given these 3 equations with these energy levels. And the strategy is that I start out, I write all the products on the right and the reactants on the left, which means we flip the first equation and leave the other 2 as the same. Then we have to multiply the middle equation by 3, either to get the 3 carbons as a reactant or to get rid of the 3 CO2s. And the next one there, we need to multiply that by 2 to get 4 hydrogens or to get rid of the waters. So, and then in through that, we also cancel out the 5 oxygens, and we're left with the original equation with opposite of the first G opposite G1 plus 3 G2s plus 2 G3s. Plug in the numbers and get the answer. Does anybody have any questions with this? I would normally have a Ken quiz on this, but since you've already covered it in 161, I'm assuming you already have this skill set. So, because you covered it already. Okay, so next thing to talk about is a reversible versus irreversible process. And this is, you see this very frequently in thermodynamics. And each step is reversible. So let's say this is known as the reversible expansion of a gas. So if we have a gas here with a piston on it, and we have sand on it, we can take off a grain of sand. If you take off a grain of sand, it increases ever so slightly. And if you add one back, it'll go ever so slightly in. And as you slowly remove it away, you can make the gas increase, and you can also add more and it can decrease. That's called a reversible expansion compression. The truth of the matter is not really any process is reversible, at least without any penalty, penalty meaning energy. So because there's a little bit of friction against the wall here, for instance, you're losing energy that way. So, but each incremental step is considered to be reversible. So it's kind of like if you have a teacup and you drop it, like, well, it's going down. It could go back up. You know, it hits the ground. Like, oh, well, this crack forms, and maybe you can say, oh, if I put the atoms close to each other, it would form a bond. You know, and you can keep on going, and then of course, you know, a broken teacup doesn't turn back into a teacup. You can't reverse time's arrow on a macroscopic process, but you can do it on a very short process, and that's known as reversible. So same thing with heat transfer. Q is heat. Heat transfer can be reversible. Truth of the matter is, nothing is reversible. Everything is irreversible. How do we deal with that? When we take other thermo classes, you just have to multiply by some factor. It's some sort of efficiency factor. Okay, so, but this is something you have to worry about other classes. You don't have to worry for this class. So, non-standard. We talk about standard. What about non-standard? Our non-standard delta G is the standard delta G plus the term RT natural log Q. Q is the reaction quotient. So R is the gas law constant. It's just, yeah, it's Boltzmann constant times Avogadro's number if you're really, really wondering what it was. Okay, but if you like graphs, maybe this can help you understand something. So if you, with this non-standard state, what's going to happen? Well, if you're at equilibrium, delta G is 0. Oh, you can barely see that, can you? Man, okay. Sorry, you can barely see this. Even it's a little better. When you're at equilibrium, delta G equals 0, and specifically, the reaction quotient equals the equilibrium constant. So it depends also how you write the equation. I can't see how you write the equation. So okay, so it's liquid going to gas. So this means in this stage here, so liquid going to gas, the delta G is negative, so that means that more water is going to evaporate. So we're going to have more water evaporation. The other one here, we have we have too humid of an air, and then it condenses down. So I always got the numbers more than the graph in this one, to be quite honest with you. But the other way you can look at it, so for me, when I look at the numbers, the delta G reaction, so if, I guess I can, okay, so the delta G reaction up there, if Q is really big, then the reaction is going to proceed towards the products, towards the reactants. And if Q is small, it's going to proceed kind of to, well, then again, it also depends on how you write the equation. It's very, sorry, I should be careful what I say. It's, much I hate to say, it's contextual. But if delta G is in fact at equilibrium, these two terms will cancel each other out. The delta G reaction, we haven't covered that yet. Shoot, no wonder it doesn't make any sense. Delta G0 is equal to minus RT ln K. We haven't covered that yet. So if minus delta G, minus RT ln K plus RT ln K is 0. So if Q is larger than K, that means delta G is positive, which means it'll favor the reactants. And if delta G is negative, I'm sorry, if this RTLNQ is a minus number, it's a bigger number than, I'm sorry, if it's a smaller number than K, it'll favor more of the products. Okay. Kind of sort of makes sense? Not really. I kind of fumbled my way through that one. Okay, so, well, let's use a non-standard. The non-standard is an important equation. This one here, and this is another one that you get. You don't have to memorize it. This one here, you'll get it. You don't have to memorize it. It's going to be important when we talk about electrochem. So let's look at this reaction. So so 2 nitrogen monoxides plus oxygen makes 2 NO2s. The delta G for the reaction given is minus 71.2 kilojoules. What is the delta G for these conditions? 0.1 atmosphere for NOO2 and 2 atmospheres for NO2. So is this more or less spontaneous? So first thing, the Q is the products over the reactants raised to the power. So in this case, it's going to be the pressure of NO2 squared, because there's a 2 there, pressure of NO squared, because there's a 2 there, and pressure of oxygen. So the Q, this is going to be, well, actually, I'll put it in the equation. So delta G 0 minus 71.2, actually, I should just write it out, 200 joules. I always like writing it out, plus R, 8.314 joules per mole, mole Kelvin, temperature 298 K, natural log of Q, NO2 squared, so 2 squared all over 0.1 squared, 0.1. No, that's an easy one. This is 4,000. 2 squared is 4 all over 1/1000th. So 4 divided by 1/1000th is 4,000. How's that for Rain Man skills? So joules per mole. So the kelvins cancel there. Plus 8.314, 298. No, it's not even K.
Oh, but wait, you didn't show the steps.
I what?
You didn't show the steps.
Which ones?
Why had it put this?
4 over
I'm
1.
kidding.
Okay. Okay, that's joules per mole.
Was that like a midterm today or something?
What's that?
Midterm tomorrow maybe? Everybody's studying for?
Yeah,
Oh,
they're
really?
not there. Well, Eric is hit or miss.
Chantel and Josh.
Oh yeah, yeah. Usually.
Yeah, but Eric, Chantel, and Josh really stick together, so I don't know what they're up to.
Maybe they like the videos you put in there.
Oh, maybe.
Well, they've been coming. Even, well, Eric just said he liked the one that was for the midterm, for the whatever midterm review.
The one with the old midterm?
Yeah. So, calculate them all out, you get negative 50.7 kilojoules per mole. So that means it's less spontaneous, because it's a smaller negative number. Okay, so recap for this one. We have this equation, we're given the standard, we want to know what the delta G reaction under these non-standard conditions are. So we employ this equation, the delta G is delta G0 plus RTL and Q. Q is products over reactants raised to their respective stoichiometric powers. And then we put it in, delta G0, and I always put it out by 1,000 because I always forget that. So that's my own reminder. RT, natural log of Q, which is 4,000. And then we get negative 50.7 kilojoules per mole. So negative 70 to start off with, negative 50 under these conditions. It means it's less spontaneous. Questions with this one? Okay. So methanol liquid going to methanol vapor. Delta G is positive 4.3 kilojoules. What is delta G, the Gibbs free energy, at 0.2 atmospheres and 298 Kelvin? Hint here, the Q is just plain old pressure of methanol, which is 0.2. People are still working, but does anybody get stuck? People are looking up. Or 2 people. Okay. Sami Billing gets A. Billing gets B. All right. Oh, cool. So everyone voted B. B is the correct answer. Yeah. 3112 joules. Or positive 0.3 kilojoules. Okay, cool. Awesome. Doing just fine then. Okay. So there's another equation, delta G 0 equals minus RT natural log K, the equilibrium constant. So this is nice, like I said, you don't even have to go in the lab anymore for this stuff. You can just outright, you can calculate the stuff based off of Gibbs energy. So what is the equilibrium constant at 298 Kelvin for this equation, N2O4 in equilibrium with two NO2s. And we're given the tables there for N2O4 and NO2. So we have to employ the previous hint, like with the so we have products. This one here, actually here I can just copy it. We can solve for this. So the products is 2 GNO2 minus G N2O4 equals 251.3 minus 99.8, which equals 2 times 51.3 minus 99.8. And this equals 2.8 kilojoules per mole. And then we can then apply this. So if delta G is equal to RT ln K, so I'm going to write this out. Delta G0 is RT ln K. We can divide both sides by minus RT. And then we can take e to both sides minus delta G for RT equals e to the ln of K equals K. So which means then K equals e to the minus delta G0 to 0 for RT equals minus 2,800 joules. Well, I'm sorry, E to the R is 8.314 joules per mole Kelvin, and then 298 Kelvin. So joules cancel, Kelvins cancel. Oh, actually, this is, and actually per moles. I'm sorry, I should have put per mole. And the inverse moles cancel. And you just get a number. So whatever, e to the minus 2,800 divided by 8.314 divided by 298. That is, and this equals K equals 0.323. How many sig figs we got? Oh, 3. Okay. So our equilibrium constant is 0.323. So that's kind of nice. You can just do it calculation-wise. You don't have to do any experiments. You don't have to leave the comfort of your internet connection. So again, this is something only humans can do. Siri can't do this for us yet. Maybe we'll get an AI that will start doing chemistry for us, and then I'll be out of a job. Okay, so recap for this one. The point of this example is to illustrate this equation. The delta G is equal to minus RT ln K. So to show how Gibbs energy and equilibrium are interchangeable, and we can use tabulated data to get delta G. So we use tabulated data to figure out the delta G for this reaction is positive 2.8 kilojoules. And then we throw that in, and then we can rearrange delta G0. We can flip to solve for K. K is e to the delta G0 over RT. We put in the values, and we get K is about 0.3. So questions with this one? Okay, so the last thing I want to talk about is just another equation, and there are actually no examples about this equation, but you've been probably so familiar in using equations like this, it's easy. So if delta G0 is equal to the minus RT ln K, delta G also equals delta H minus T delta S. So you can take this RT and you can put it there and divide it like you're doing in this equation. And then you have, so the ln K equals minus delta H over R inverse plus times inverse temperature plus entropy over R. But then you can do the 2-point equation. You can have K2 and K1. You can take K2 and subtract K1 from it, and then you can get a 2-point equation like this that will get rid of entropy completely. And you can use it to solve other things. But I don't even know if that's on the final. I have to check. But it's just another equation you might be able to use. But with that, we're getting good. Oh, we're done a little early. Does anybody have any questions with this stuff so far? Students usually like thermo. I think it's boring as hell, but it's useful. It makes perfect sense, which angers me because it's so boring. I think like quantum mechanics and like things bonding and how they react. I think that's cool. That's the kind of fun stuff I think is cool. I don't like this. I have a friend who's a thermodynamicist. He's actually an interesting person. Just what he studies is boring. Not that he, So on Monday, what is today? Wednesday? On Monday, we're going to study how to balance oxidation reduction reaction. So this is a day not to miss because students have a really hard time, and I have a good lecture prepared for you. That's one of my how-to lectures. So anyways, I think I'm done talking. Anybody have any questions? Okay, well, I guess we can start doing the problem session. You guys, yeah, I'll stop recording. I shall stop this. Okay.